Hi there. I hope you're having a good fall break. So this is going to serve as our lectures over the next few days while I'm gone in Amsterdam. Today we're going to be talking about priority queues. This is just kind of an introduction. We're going to talk about the API and the elementary implementations for it, and then later we'll talk about a more sophisticated way to do it, which has better runtimes. So in general, collections that we've already talked about, a stack and a queue, they have the key operations push, pop, enqueue, dequeue, and underneath them, the sort of the underlying data structure could be either a linked list or a sizing array. And we talked about the different ways that we can handle that, the differences being in memory use and runtimes, one being constant, guaranteed, and one being amortized. Today we're going to talk about priority queues, which have similar key operations, insert and a deletion, but this one's going to be either delete max or delete min, depending on which priority queue we're using. And the data structure we're going to build up to eventually is a binary heap. But some other collections that we may touch a little bit on are symbol tables, so being able to put into a symbol table and be able to get out and delete a specific entry. But also a set. So a set either contains an element or does not contain an element. And both of these, a symbol table and a set, can be implemented using a binary search tree or a hash table. And we will spend a little bit of time talking about them as time goes on. All right, so here's a really fun quote from Fred Brooks, which, by the way, did come and visit Taylor. And just outside of the CSE department, we have a quote of his up on the wall. But anyways, here's a quote from him. Show me your code and conceal your data structures, and I shall continue to be mystified. Show me your data structures, and I won't usually need your code. It'll be obvious. So what this is trying to say is that when you have a more sophisticated object type, the code itself is just kind of gluing together the data structures, but really the data structure used within that object kind of describe how that object is used and how it can be manipulated, and that tells a lot more about what it is that this object can do than just simply looking at the glue that holds everything together. Okay. So here is the priority queue. It is a collection we can insert and delete items from, but now the question is, which item do we delete? With the stack, it was the most recently added item to it. With a queue, it was the least recently added item. With a randomized queue, we're just going to pick one at random. But for a priority queue, we're either going to remove the largest item or the smallest item, depending on which priority queue we're using. If it's a max priority queue or a min priority queue, we'll remove either the maximum item or the minimum item, respectively. So in the code example here, we have a bunch of items being added on, and then after we add on a few items, maybe we want to remove the maximum item given. So if we insert P, insert Q, insert E, and then we call to remove the max, well, over all the items that are currently in our collection, P, Q, and E, the maximum item here is Q. So that's the one that gets removed. Then we insert X, A, and M, and we do a remove max. At this point, we're going to look over all the items that are currently on the queue. So P, not Q because that was removed, E, X, A, and M, and out of all 5 of those, X is the maximum item. And then continuing on, P, L, E, going on, remove the max, and it's, well, we actually have 2 of them. We have 2 P's. They're both max. One of them gets removed. So here is the general API. And we do want this to be a generic so that we can put anything that we want onto it, which means that all the items need to be comparable to each other. So we have here is the definition of max, or the API for a max priority queue. We're going to take a generic type key, which extends comparable key so it can compare to one another. We'll have just a blank constructor, which creates an empty priority queue. We'll have a max, another constructor that takes an array of keys, so it can automatically put entries in there rather than having to insert them one at a time. We can insert one key at a time. We can delete an item which returns a key, and that is in this case, the largest item currently on the priority queue. And similar to our other collections, we had is empty, which just returns a true or false if it's empty, a max, which returns the largest item that's on there, and then a size, which returns the number of keys are currently stored on the priority queue. And one thing that's important, duplicate keys are allowed. Similar to our previous example, we had at the end here, we had removed the two maximums so far, so it was the Q and the X. Those are removed. We have a P as the current max, but we do allow another P to be put on. In this case, whenever we do a del max or a max, we just pick one of the maximum keys. It doesn't really matter at this point. Maybe we can specify more strictly which one gets removed, but in this case, we're just going to say either one. Doesn't matter. They're both max. All right, so applications of priority queues include a lot of things. It is a fundamental type of computer science, and so it is used all over the computer science programming. So event-driven simulation is a fantastic use of priority queues. So we have different customers in line, colliding particles, so knowing when the next collision is going to occur. Numerical computation is another application, so reducing round-off error. Discrete optimization, bin packing, scheduling. Another one, which is one that our next project is going to be over, is called A-star search, which is very related to Dijkstra's algorithm. Web caching is another example of this. Any sort of caching that has some pieces of data that might need to stick around for a little bit longer than others. So having just the least recently used algorithm may not be the most efficient for certain types of applications. So it may be useful to have actually a priority queue instead. Operating systems for load balancing, knowing when a program should have a higher priority, be allowed to take over the core or the thread to start execution, to be able to handle interrupts. Huffman codes is another great example of using priority queues, and then many others. Okay, so here is an example. We haven't really talked about how we're going to implement this yet, but let's talk about an example of how to use it and start thinking about, okay, what can we do to what can we use to implement something like a priority queue? All right, so here's the client. Find the largest m items in a stream of n items, where n is just huge. We're talking like it's too big to even fit into memory, but also m is large potentially. So we need to be able to be efficient with our memory use. And because n, the total number of items that we're going to be working with, is so big we can't fit into memory, then kind of the trivial implementation, which is just storing all n items into memory, sorting them, and then taking the top m items is infeasible. We just can't do this. So an example of this is detection of fraudulent transactions. Typically looking for large transactions in among many transactions. So I would argue that most of the transactions probably are in the low dollar range. So you think like going to Starbucks and picking up a cup of coffee. But here we're interested in finding very large money transactions. Another example of this would be NSA monitoring. So there's a lot of documents flying over the internet, email, and so on. We want to just mark the most suspicious looking ones among all of the data that's flying so that we can have a human go and take a look at what's going on. So just a reminder, n is big. It's way too big to even fit into memory. So we cannot store all the values, sort them, and return the m smallest ones or the m largest ones. We just can't do that. All right, so for example, down here, I have a simple text file that contains a bunch of transactions. So Turing made a transaction on this date for this amount of money. Von Neumann made a transaction on this date for this amount of money, and so forth. So we have a whole bunch of these transactions. And what we would like to do is feed all these transactions into our top M program, along with the number of items that we're wanting it to spit out. And it will return to us the top 5, the maximum 5 transactions that happened. Okay, so here are all of our N entries down here. And among all of these, we want to find the maximum 5 entries in here. In this case, we're sorting on the last column, which is the amount. We don't really care about the last 5 dates, the last 5 transactions that happened, or even the person with the last 5 names alphabetically. So here we're focusing in on just the dollar amount of the transaction. Now, one thing that's an interesting note is what happens when m is equal to 1. So when m equals 1, that means that we're trying to find the one largest entry out of all n entries, which is a max function. So there, that one's a pretty trivial implementation. We could just scan through the entire thing and keep track of which is the largest one that we've seen so far. So we'll start off, this is the largest. Oh, that one's bigger, so we'll keep a finger on there. This one's smaller. Oh, this one is bigger, so we'll go ahead and go there. Smaller, smaller. Oh, that one's larger. Smaller, smaller. Slightly larger. Smaller, 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 smaller. And so we could just simply return Thompson. Okay, so that's one way to do the max where m is equal to 1. Well, what if m is equal to 2? Well, one approach is, well, we can go through, find the maximum item, and then go back through the entire thing again and find the new maximum with this entry removed. That's an approach, okay, so that we can run through it twice, through a list twice, and be able to return the top 2 entries in there. Well, what if m is large? And this is where things get interesting. So when m gets large, we don't want to run multiple times through it, because then our runtime creeps up to what, n times n, n squared, right? So we don't want that to happen. So instead, we want to find something that is a little bit better running than this. Sorry for the jump cut. Yes, n times n. I just had to think through that solution. Okay. I also wanted to pause it to make sure that I was going to be able to put together the clips for you to make a nicer video for you to be able to watch. Okay. So in the end, we want to find something that runs better than n squared, than just running through it multiple times, always finding the max item and the next max item and returning that. Okay, so here would be an implementation of that exact client that we saw on the previous slide. So this is our top M implementation. So we're going to create something called a min PQ, and even though we're looking for the maximum items, hopefully this will make sense in just a moment. So we're going to have a min PQ of transactions, and we're just assuming that the transaction knows how to handle the multiple entries. We have name, date, and then amount. And that it's also comparable. It knows how to compare transactions to one another. So we're going to create a minimum priority queue, we'll call it PQ, of these transactions. And while we still have lines to read in, we're going to read in the line and then create a new transaction on the line, again, assuming that it knows how to split up the entries, the name, the date, and the amount. And then we're going to insert them into the priority queue. Okay, so that's all fine and dandy. So this is going to give us access, because it's a minimum priority queue, it gives us access to the minimum item on the priority queue. And we can delete that one item very efficiently. Deleting other items we might be able to do, but it'd just be more expensive. All right, so why a minimum priority queue? And this is where the min PQ comes in, even though we want to find the max 5 or max M entries. So every time we insert, we're going to check its size. And if the size is ever greater than the number of entries that we're looking for, so say 5 or 10 or whatever, we're going to delete the minimum entry that's on there. And so after each insertion, if we're above our M, so we have M plus 1 entries on there, we're going to find the smallest item that's on there and remove it from the priority queue, leaving behind the current M largest entries on there. And so after we're finished processing all of these, it'll have the top 5, or the maximum 5 or maximum M entries over all of the data that was in there. Okay, so here again, this is just an implementation for this example on this slide. All right, so 2 trivial ways or 3 trivial ways to implement this is, well, one, this priority queue can just simply have an array inside, or maybe a linked list that allows us to insert in constant time, possibly. So if we're always inserting at the end or at the beginning, at the end for for an array, at the beginning for a linked list, maybe we can have pointers at the 2 ends. We can put on either end for the linked list. Then we're able to insert trivially. So putting in a new item just gets put into the array or onto the linked list, inserting another one. But here comes the problem. When we want to delete or even just know what is the minimum item that's on there, we have to scan through all the entries that are on there to be able to know which one is the smallest. So insertion can be done in constant time, but deletion will take time corresponding to the number of entries that are on there. So it could be up to n items on there. So it at worst is linear to the number of entries that we've already inserted. Okay, so this is with an unordered array or linked list. Another approach to do this is, well, what if instead of just putting it at the end, we put it in the correct order, either in order, so the smallest ones at the beginning, or in reverse order, so the smallest ones at the end. So now we have constant access to the largest or the smallest entry on there. Just look at the 2 ends. But the problem now is, how do we put it in the right place? With an array, we have to shift entries over. If the new entry goes in between 2 items, so here we're inserting an M, it needs to go between the P and the A, or the A and the P, depending on the order that we're choosing, which means we have to shift things over to make room for this M. For a linked list implementation, that's a lot easier, but we still need to find where does that need to go, which that also is linear. So with an unordered list, we have constant insertion, but linear deletion. For an ordered list, either forward or reversed, we have linear insertion, but constant deletion. So both of these are not really good. In fact, they're not much of an improvement over our previous implementation, where we just run through it multiple times and always return the min or the max item depending on which one we're going. So this is not an ideal way to implement this, but it is an approach that we could possibly use. There's better ones. All right, so this table here just shows what we just discussed. Insertion on unordered array is constant. For deletion, it's linear. Even finding the maximum item is linear. For an ordered array, insertion now is linear, but deletion and max or min, if we're using min priority queue, are constant. The goal for this slide deck is to get this down to logarithmic time to the number of entries that are in there. So that is the goal. So hopefully you can see that with this log here, we're probably going to be doing some ordering. So it's going to look a little closer to a binary search. So remember, anytime you see logs in there, that's probably an indication that we're doing like some divide and conquer like approach to this. And that's actually how we're going to implement it but probably not quite like how you think. All right, so let's talk about something called binary heaps. All right, so first, to talk about binary heaps, we need to talk about what a binary tree is. A binary tree is either an empty, so there's nothing there, like a null, or it's a node with two links, one to the left and one to the right. And both of these links reference other binary trees. So we can have just the trivial, I have a new feature here I'll show off. We can have the trivial empty, so there's nothing there. Or we can have a node that has left and right links to other binary trees, which they can be empty, same as before, we have a recursive definition, or it can be a node with left and right binary links to binary trees. And this can just go on and on and on. All right, so that's a binary tree. Just a general, we have two directions, either empty or it's a node with left and right links to other binary trees. The next definition we'll have to cover is something called a complete tree. And a complete tree is a perfectly balanced tree except for the bottom level, which means that for every link in a binary tree, this would be left and right. We can have a tree that has 3 nodes or 4 nodes or however many nodes we need. But the important thing is that the left and right, or all the links pointing down to its children, are full. So there is a node there, except for the very bottom level. Okay, and we're going to state also that all of the nodes, all of the additional nodes at the bottom need to be shifted left to the leftmost position here. That will make a little bit more sense in just a minute when we talk about the implementation for it. But for now, just know that this tree up on the top is completely full. The only thing is the bottom row can have some empties, but they all have to be to the right of the last node here. Okay, so a complete binary tree has this sort of structure here, and an example of if there are exactly 16 nodes in this tree, that means that its height, so the number of edges from root 1, 2, 3, 4, the number of edges to traverse from root to leaf is equal to 4. And we can compute this as just the floor of the log base 2 of n. And the proof that this is the actual height of a complete binary tree is given that whenever we increase the number of entries on there, the height only increases when n becomes a power of 2. So if we don't count this last node down here, so if we do, say, here we have 1 node, but as soon as we add the second node, 2 nodes now is a power of 2, so our height increases from 0 to 1. And then we can add another node without increasing the height. But then the next node we add, so we have 1, 2, 3. The next node we add is 4. That is a power of 2. We have increased the number of edges that we have to cross to get from root to leaf. So this is 4, 5, 6, 7. And as soon as we add the next one, which is also a power of 2, we have increased, again, the height of the tree. So it only increases when n is a power of 2. Okay, here's an example of why God loves binary trees. Yes. All right, so this is fine. You probably are thinking, well, we could just do this similar to a linked list. We can actually have a node object with left and right links, the reference node objects, and just set nulls in there if they're pointing to empty. But similar to the linked list implementation compared to the array-based implementation, the amount of memory, the additional memory that we have to store can be rather large, so a factor larger. Plus, there's a lot of overhead involved in traversing the linked list. So instead, what we're going to do is implement this using an array, which does mean that we have to potentially increase the size of the array as we go, so we have to pay the amortized cost. But if we know how many entries are coming in, or at least how many entries we want to limit our priority queue to, we can benefit from the array-based implementation and not have to pay the amortized cost. We just allocate an array large enough to begin with. All right, so we're going to talk about the array-based implementation. First thing to note is that in this implementation, we're going to start counting at 1. I know this hurts some of you to even think about this. We can start at 0. It's just the math works out much nicer when we start at 1 than with 0. So there we go. All right, so we are going to start our index at 1. And in this implementation, we're going to take the nodes in level order. Okay, I'll explain what that means in just a moment. But when we do this, when we put our nodes in level order, the children of some node at index k, the children of this, and for the binary tree, a complete binary tree, the children for the kth node is going to be located at 2k and 2k plus 1. And the nice thing about this is we can actually do away with any sort of explicit links. We already know, given a node's location, we can compute exactly where its children are going to be at any time. So we don't even need those references. So you think back to the linked list, we had the node object, which was basically just a wrapper of the item. So inside that node, we had a reference to an item, but we also had a reference to the next node. So we're paying the overhead, the 24-byte overhead, to create the node, and then we have additional 8 bytes to reference the next node. So we're paying 32 bytes of overhead just to do that. 32 bytes for every entry that's on there. With this array-based implementation, we don't need that reference to the next one, so we can remove the 8 bytes. Plus, we don't need a node for every item as sort of a wrapper, so that 24-byte overhead goes away. So we just have the 8-byte reference to the item itself. We still have to pay that. Plus the slight overhead in the array, but that's independent of the size of the array. So in other words, we're going from 40 bytes per item down to 8 bytes per item. So it's 5 times smaller, which is really useful. And again, if we know the size of the priority queue going into it, or we know how many entries are going to be in the priority queue, we don't even have to pay the amortized cost of increasing the size of the array. Okay, so this is the array-based implementation. I still haven't talked about the level order, but we are starting our index at 1. Okay, so here is an example of a binary tree, a visual representation of a binary tree, and this would be its array representation. So at the root we have a T, we have an S, an R, P, N, O, A, E, I, H, G. And you notice that I read them off in level order. I started at the top, read all of level 1, then read all of level 2, then all of level 3. That's level order. So in our array, we're skipping the 0th entry. We're starting at index 1. But at index 1, it's the root. And at indices 2 and 3, we have this second level. We have S and then R. And then the next level, P, N, O, A. And the next level, which is incomplete, so O and A do not have any children. We have E, I, H, G. Okay? So going back to this slide here, the children of some node K are located at 2K and 2K plus 1. So if we come here and we wanted to know what are the children of, say, node R. Well, item R is located at index 3, and so its children are located at 2 times 3, which would be at 6, which is here, and 2 times 3 plus 1, which is here. Okay? And if we happen to fall off the array, for example, if we're looking for the children of O, it has no children here, but O is located at index 6, and its children, if it were in the tree or in the array, would be located at index 12 and 13. But since it's beyond the length of our array, we know that there are no children for O or for A, or for any of the entries down at the bottom level. So there is our how you convert from a complete binary tree to the array-based implementation of this. And then hopefully you've seen this, but just in case you missed, the reason why we want to move all of these this bottom level to the left is so that we don't have any spaces here. We have no gaps in here. In fact, this is a very tight implementation. It's a very tight way of storing it. There are no entries that are left open. Okay, and there's some other reasons that we'll talk about here in just a little bit, but that's one of the nice ones. Okay, so here's a quiz. What is the index of the parent of an item located at index k in a binary heap, a complete binary tree? So if we're looking for the parent index of an item located at index k, what would that be? So here is a visual representation of the same thing that we had from the previous thing, and I've gone in and added the indices for each of the items, but here is also the array-based implementation. So I'll give you just a moment to think this over. You can pause if you need a little more time, but I'm going to go ahead. So the item located at index k, its parent, so say this one right here, its parent is going to be, for this, 5, its parent is 2. But also P's parent, which is 4, is also 2. So we're going to have this k over 2, but the question is it minus 1, plus 1, none of the above? I don't know. Well, if you simply just divide by 2 and then floor that division, that gives you the answer. So B is it. I guess you could be a little more technical and say, well, none of the above. It should be the floor of k over 2. But either of those are fine. All right. So in order to implement our priority queue, we're going to use a binary heap under the hood, and we're going to use the array-based implementation of this. So the indices are starting at 1. We're going to take nodes at level order, so top level, the next level, and so forth. The children of node located at k are at locations 2k and 2k plus 1. We don't need any explicit links to the children or to its parent. We can actually compute its parent as well. We can move up and down the tree. Just doing some math, we don't need to follow any references. And so a max heap is going to be force the data to be ordered just enough so that the maximum item that's been inserted on there and hasn't been removed will be located at the top of the binary heap, and that each of the children for every node that's in there will be the children will be no larger than its parent. So a parent's key is no smaller than the child's key, and I have an example of that. And so there's just enough ordering of the data in here allows us to be able to access the maximum item that's in there, but it doesn't force all the data to be totally ordered. So we can actually get by with doing insertions into this data structure in less than in log n time, which is kind of cool. All right. So a binary heap is an array representation of heap ordered complete binary tree. All right, so it's just enough ordering, gives us the support we need to be able to efficiently implement the priority queue operations that we're interested in. So the largest key is going to always be located at A sub 1. That's the root of the binary tree. And we can use the array indices to move up and down the tree as we need. So the parent, the children of a node at k is 2k and 2k plus 1, and the parent of a node at k is k over 2. Technically the floor of k over 2, but that's fine. And then what about insert and del max? So this is getting the maximum item, but how do we insert and delete? Well, we're actually going to just put it into the array in a place. We're going to manipulate the array in such a way that it's efficient for us to do that manipulation, but it's going to violate the heap order. So we're not going to maintain that the parent's key is no smaller than its children's key for just a moment. So we'll violate this so that we can efficiently insert or delete, and then we'll have to fix up the array to put it back into heap order before we move on. All right, so here is a demo for doing that. So we want to be able to insert an item into the structure, and then we're going to remove the maximum item from the structure. And the way we're going to do this is insertion is going to add an entry or a node at the end of this. And because this is a complete binary tree, we're going to find the node on the second to last level, or maybe the last if there's no if the last level is completely empty. We're going to find the one that has, the one that has 0 or 1, the last entry that has 0 or 1 entries in there. So in this case it is H. H only has 1 child, so we're going to insert to here. All right, and when we do that, so if we're inserting into here, that's fine if its value is actually smaller than H, but what happens if it's larger than H, right? So say we insert an X in here, and X should be up at the top, but right now we're inserting at the bottom. So when we insert, we're going to put it here because it's cheap to do that. We could just simply insert it into the array at this location, but it violates the heap, and then we'll have to fix it by swimming this entry up the tree. So I'll give a short demo in just a moment. The other thing is removing the maximum item. To do that, so suppose we're wanting to remove the max item, in this case it's the T. What we're going to do is we're going to swap the entry at the root with the last entry here. So we're going to swap these two values. So we're going to put G up here, T down here. With T down here, T here, we can just simply remove it in constant time, so we're good to go. But this violates, obviously, this max heap. Now a small item is located at the root. Possibly these entries here are larger than this, so we need to fix the heap. And we're going to do that by sinking the entry down. So I'm going to pause for just a moment. All right, had to get a drink. Okay, so let's talk through the binary heap demo. We have, again, we're going to be inserting new entries, and they're going to go at the bottom, and then we're going to swim them up. And then when we want to remove a maximum item, we're going to swap the root with the last entry that's in there, and then sink it down to its correct spot. And I had mentioned that we're going to find, when we insert, we're going to find the entry in the second to last row, maybe the last row if there's if the last row is completely full, that has 0 or 1 children. So the first entry in there. This could be the first entry, excuse me, that has exactly 0 or 1 entries. So if you go through, T has 2, P has 2, R has 2, N has 2, H has exactly 1. So it's when we go to insert, this is where the next entry is going to go. So this is another way to kind of describe it. It's probably a little cleaner that way. I should have said it that way the first time. Okay, so here is the demo. We want to insert S into our data structure. So again, S is going to go in at the end, which is efficient to do assuming we have an open spot in our array. So S is going to go in at the end, which is going to be a child of H. But notice that S is larger than H, which violates our maximum heap. So we need to swim this entry up. So we're going to swap H and S, and we know this, again, looking visually here, but this S is at index. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So its parent is at floor of 11 over 2, which is 5. 1, 2, 3, 4, 5. So this is the H. H is parent. So we're going to compare the entry at S and at H. And if this is smaller than this entry, then we are going to swap them. Okay? Now we do that swap, but we still might be in violation. So we can move this down without any issue, because every parent has a key value that's not smaller than any of its children, including its grandchildren and great-grandchildren and so forth. So we can move it down like this without any issue. But moving S up, it might still be in violation with its parent. So now S is located at 5. We look at S's parent, so 5 over 2. The floor of that is 2, so 1, 2, so its parent is P. We compare S to P. We see that S is greater than P, so we need to swap them again. And when we've done this, we could check S with its parent. So S is at 2. 2 over 2 is 1. So S compared with T is larger than S. So we're in good order here. So we don't have to do any more swapping. So recap, we inserted at the bottom and then we swam S up to where it was no longer violating the maximum heap constraints, or the invariance that we hold for the maximum max heap. All right, so that's inserting S. What if we wanted to remove the maximum item? In this case, the maximum item is located at the root. This is T. So how do we do this? Well, the first step we're going to do is we're going to swap the root with the last entry. So we're going to swap the root with the last entry that's in our array, our binary heap. So we swap them out. And now we have the ability to just remove T efficiently from the array. We could just set it equal to null, and we're good. But in that swapping, we've moved a low valued item up to the root, which might be in violation of our invariant. In particular, H is, in this case, both smaller than S and R. Okay, so we need to sync this down. And in order to do this, we're going to swap it with one of them. Which one? We'll talk about that in just a moment. But we're going to swap it with one of those. So we move it here. And repeat. So now we need to check, is H smaller than N or P? It is. It's smaller than both of them in this case. We need to move it down. And then we check it again, check H with its children. Now notice that H is located here, which is 1, 2, 3, 4, 5, index 5. So its two children are 10 and 11. So this is 5, 6, 7, 8, 9, 10. So it's we compare it with G, but we also compare it with 2K, 2 times 5 plus 1, which is 11. So notice that we've deleted that last entry off. Our size is only including these. So in this case, H only has one child. But in this case, H is greater than all of its children, so we don't have to do anything with it. So at this point, we are done. So we have effectively inserted a new entry and then deleted the max from the entry. What if we do it again? What if we called remove max a second time? In this case, we want to remove the S, so that we're going to swap S with G. We can remove S, and then we need to sync G down into its correct spot. And at this point, we're finished. And if we try to insert another entry again, in this case, we're inserting the value we just removed, so S. So previously our S, I'm going to back up just a little bit, our S was located at the top because it was the maximum item. We removed that maximum item, so now our new max item is R, but we're going to reinsert to that S. So in the end, it should go back up to the top. All right, so to do that, again, we're going to place our S at the bottom, which is as the left child of H gets inserted. That may violate our invariant, so we need to swim it up until it's in correct position. We're no longer in violation, and we're finished. And that's it. So that's how we insert and how we delete. And obviously getting the maximum item is just looking at the item at index 1. All right, so the act of swimming up is called also promotion. So this is where a key becomes larger than its parent. So when we insert at the bottom, and we need to promote it up the chain. We need to swim it up. We do this to be able to eliminate the violation. And we do this by exchanging the key in child with the key in parent and we follow the child on up through the parent and so forth until the heap is restored. And so this, we're going to use a helper function, define a helper function called swim that allows us to be able to do this. So we're going to potentially swim the kth entry up until we're no longer violating our max heap invariance. So while k is still greater than 1, so 1 was at the root, so while we're not at the root yet, and the entry at the parent of k compared to k, so the entry at k over 2, k's parent, while that is less than the entry at k, we want to swap it. So in other words, if the parent is smaller than the child, we want to swap child and parent. So we're going to exchange these two entries, and we're going to follow the child that's now the parent. We want to continue following it up. So we're going to also divide k by 2 to follow up the chain. So this is our helper function swim that we will use to help us with insertion. So here is an example. Here we have, we're in the middle of some action being performed, but the important thing is we have a violation. We have a parent with a value of p, which is smaller than its child, which has a value of t. So we need to exchange these two, and in fact we need to exchange t up clear to the top because it's even larger than s. And so after we've swam it up twice, it is sitting at the root, but now we are back in proper heap order. All right, so insertion looks like this. It's very simple. We're going to add the node at the very end and then swim that entry up. So in other words, we're going to insert some key k. We want to first increment n. So we're going to add a new entry onto here, and we're going to assign at that location this entry that's in there. So n is the number of entries. We increment it by 1, so we have one more entry. This is kind of assuming we still have space. We have enough space in our array to be able to do this. But we're going to increment n, place k there, and then swim that entry up until we're no longer in violation. So the cost of this is at most 1 plus log base 2 of n comparisons. Why is that? That's because we are using a binary heap, so that's where the log base 2 is, but it's also a complete binary heap, which means we have no gaps. And we showed way back at the beginning that the height of a complete binary tree increases only when n becomes a power of 2. So we have a limit on the height of the tree, which is log base 2. We have the plus 1 comparisons to get it potentially all the way to the top. So at most, inserting a new entry will be 1 plus log base 2 of n, which is kind of cool. We can insert in logarithmic time, which is fantastic. So compare that to our previous the naive implementations where you had an unordered or even an ordered list. And with the ordered list, we can do a binary search to figure out where the new entry needs to go, but then we need to shift all of the entries over, which may cost us linear time. Now we can insert in log time, log base 2 time. So that's kind of nice. All right, what about? Oh yeah, here's the description or visualization of insertion. So we're inserting S. This violates this relationship. We have a parent that has a smaller key than its child, so we need to swim it up. And once S reaches this position here, we're back in proper heap order. All right, so what about with deletion? So in order to delete, we need a little similar to swimming that was a helper function for insert. We need a helper function for our deletion. And this one's going to be the opposite of promotion. We're going to have demotion. So this is sinking the entry down. A key becomes smaller than one or both of its children, so it needs to be demoted. One of its children needs to become the parent, and the parent needs to become the child. And we're going to do this to be able to eliminate the violation. We're exchanging the key in the parent with the key in the child, with the larger child. And I'm going to leave this to you to figure out why not the smaller child of the two. But when we're looking at the example of demoting or removing or sinking down the entry, and we had the two children that were both larger than the parent. We picked one of them. In this case, we're always going to pick the larger of the two. And I'm going to leave it up to you to figure out why that is. But we're going to continue to do this until the heap is back in proper order. So our implementation looks like this. We're sinking down the kth entry. So while 2 times k is less than n, so in other words, our kth entry has children, at least one child. If it has 0 children, then it's not in violation, so we don't have to sink it. But if it has at least one child or 2 children, it might need to sink down. So while we still have children to compare to, we're going to find the entry of the first child, so that's just 2 times k. And we're going to check to see if the left child is smaller than the right, smaller than the right child. And if it is, we're going to select the right child instead of the left child. But we still have to do this comparison to make sure that we have that parent node has 2 children. If it has exactly 1 child, that's going to be a left child because we have a complete binary tree. All the entries are shifted, to the left there. So it'll have either 0 children or 1 child that'll be in the left side, or 2 children, left and right. So we're going to figure out which one is larger. So now J is the index of the larger child, and we're going to compare K to J. And if K is not less, so it is the parent is greater than the child, then we're going to break. So in other words, we're in proper max heap order. We're done. We can leave. Otherwise, if the parent is smaller than the child, we're going to exchange the 2 and then follow the entry on down until it's in proper order. So here's an example. We have over on the left this H parent node, which has 2 children P and S. The larger of these 2 children is S, and H is smaller than S, so we need to sink H down. When it is here, we're going to compare H to its 2 children, N and G. We're going to find the larger of the 2, which in this case is N, and H is smaller than N, so we need to swap it down, and it fits in neatly right here. And now H has no more children, so it is in proper heap order, max heap order. So we're good there. All right, so to implement del max, we're going to use the sync helper function to do this for us. We're going to first exchange the root with the node at the end, so the last entry gets put into the root position, the root gets put into the last position, and then we're going to sync this new root, which may violate the max heap, down into its proper position. All right, so we have here, we're going to put our finger on the maximum entry that's at the root. We're going to exchange the entries of the root and the last one. And then we're going to null out to prevent data loitering. We're going to null out that last item and decrement our count. And notice that we're decrementing after we null out the last entry. Then, because we exchanged the last item with the root, we may have violated our maximum heap, so we need to sink down that root into proper position. And then finally we return the maximum item that was the previous root. And that's it. So pretty simple. The nice thing about this is because our height is bounded by the log base 2 of the number of entries that are in there, that means the cost for deleting the max is going to be 2 times log base 2 of n. Why the 2 there? Well, the 2 is because of, with our sync, we are first comparing the left and right children to one another. So that's one comparison. And then we compare the parent to the larger of the 2. So that's 2. The 2 comparisons for every time that the item needs to be sunk down. And so that is why we have 2 times log n comparisons. And here is an example. So T was the root item, the maximum item in there. H was down here. We exchanged the 2, but note that now we're violating the maximum heap. So we find the larger of the 2. In this case is S. And so we're going to exchange H with S and then continue on down until it is in proper sorted or max heap order. So not sorted order because it's partially sorted. Each entry is, every node is no smaller than any of its children or its children's children. So there's some partial ordering there, but not complete ordering. And that's it. So here is the entire implementation for a maximum priority queue. Again, it's a generic type, so we specify some generic type key that is comparable to other keys so we can be able to compare them. We're going to have an array of all the keys. This is our priority queue, and have the number of entries stored in n. So the constructor in this case is a little bit different than the API that we specified, but hopefully you can kind of see how to merge the two together. Just note that when we insert, we might need to increase the size of the array, but you've already seen how to do this. It should be a rather simple implementation, hopefully. But in this case, we're just going to say allow the client to specify a maximum capacity for this. So similar to the fixed capacity array-based implementations of queue and stack. We're just doing this here. But note that we have to add 1 to it because we're starting counting, or we're starting our index into this array at 1. So we need to shift things over by 1 entry. To test if is empty, we just check the number of entries is equal to 0. And then insert is exactly the same as previous code. Delete max, exactly the same. Swim and sync, exactly the same. And then these entries here are exactly the same as what we saw for our sorting. So we have a less helper function that compares the item at ith index and the jth index to see if this ith indexed item is smaller than the jth index item. And then exchanging, it just has a temporary storing at the ith entry. It replaces the ith entry with the jth entry and then replaces the jth entry with this temporary value here. And that's it. That's our implementation for a maximum priority queue. So with this implementation, because we have a bound on the size of our priority queue, of the tree, the complete binary tree, and it's bounded by a log base 2 of n, then we have logarithmic insertion and deletion, which, even though this is greater than this constant here, is certainly much less than the linear runtime for deleting. And here, this is smaller than the constant delete max of the ordered heap, this log is certainly better than the insertion. So this is actually really good. Plus we have constant access to the max entry here. Here's a fun little challenge to think about. How would you delete not the maximum entry in the max priority queue, but some arbitrary random key in the that's in the heap, and do this in logarithmic time? So, fun little problem to try to think about how you would do that. Okay, some practical improvements for the binary heap implementation is to do half exchanges. This is similar to the half exchanges that we saw as an implementation improvement for insertion sort. So rather than swapping two values, so setting this value to this, doing the full exchange, just hold the one entry out and shift things over until you find the right spot to put in the entry. This basically halves the number of writes that you have to do. And in this case, it is definitely worth doing. It does require a little bit more sophisticated exchange function, but not really that much. It's definitely worth the improvement that you would receive. Another practical improvement is, rather than having a complete binary tree, what if we allowed it to be, have 3 nodes or 4 nodes or D nodes? And so this here is called this more generalized form is called a multi-way heap. This is a complete D-way tree. So we have every node has D children here, but we still hold on to the parent's key is no smaller than any of its children, not just the left or the right, or if it only has a left, or if it has no children. This is for any of its children. And the nice thing about this D-way is the height of the complete D-way tree is now rather than being log base 2 of n, it is now log base d of n. So as d increases, the height of the tree gets shorter and shorter and shorter. So one fun thing to think about is, why not set d to be really big? So we have a very flat tree. Then insertion theoretically is very quick, right? Because we could just insert. We don't have to swim up, or in removal, we don't have to sink down the entry very far. It's very close to the root, or the root and any particular leaf are really close together. But there are some issues with that, and that's something I challenge you to think about. All right, how many comparisons in the worst case does it take to insert into a D-way heap? So going back here, I'm going to just pop over real quick. We have the structure here we want to insert. Just a reminder, we're going to put our child, we're going to insert at the first node that has that's not completely full. So in this case, it's the I. We're going to insert into here and then swim up. So for insert, we're inserting at the bottom and then swimming up. And each time we swim up, we have to compare. So how many comparisons in the worst case does it take to insert into a D-way heap? Is it log base 2 of n, log base d of n, d log base 2 of n, d log base d of n? Maybe you don't know. I'll give you a moment just to think about it. Okay, pause if you need a little more time, but I'm going to move on. So in this case, it would be log base d of n. So remember that the height of the tree is bounded by the log base d of n, and so the number of times we have to swim up is based on that. So that means the number of comparisons that we need to do is based on that. All right, what about delete max? How many comparisons are needed in the worst case to delete the maximum item in a D-way heap. So pop back over to this example here. So deletion, we're going to swap the root item with the last entry in the array. So we're going to swap Z with O. So O will come up here. We can safely remove Z from the array very quickly. We can do that in constant number of operations. But now we need to sync down this O. This O needs to go down, it needs to compare to the largest entry among its children, and then sync down that direction. So going back here, how many comparisons in the worst case does it take to delete the maximum entry in a D-way heap? I'll give you a few moments to think about this. All right, pause if you need some more time. The answer to this, well, let's think about it. Here we have, we move this entry up, and then we need to drop it down. But in order to do that, we need to find the maximum child of all of its children. So we need to compare each entry in here to find the maximum item, which can be done by first putting our finger here. We can assume this is the largest, then look at the next one and compare. If the next one happens to be larger, we'll put our finger here, so this one is the largest, and move forward. Well, in this case, the first one happens to be the largest. But for every time we want to sync, we have to find the largest child, which means we have to compare every entry there. How many children are there at max, at worst? Well, whatever D is. In this case, it's 3. And once we've found the largest entry, so in this case it's Y, we have to compare this entry with this one to possibly sync it down. And then if we do need to move down, so in this case we have O up here at the top. O is smaller than Y, so we need to swap it down. And then we repeat this. So at every time we sync down, we have to find the next largest child, which requires D comparisons. And we need to do one more comparison to move it down. And the height of the tree is bounded by log D, so that means that our answer is D. We have D comparisons for every entry to find the largest child, and the number of times we have to repeat this process is based on the height of the tree, which in this case is log base D of n. Okay, so extending our table a little bit more, we've seen our unordered array implementation, not so good. Ordered array implementation, still not so good. The binary heap got us down to log base 2 of n, log base 2 of n, so that's pretty good. The D-array heap now gets us down to log base D of n and D log base D of n, so that's pretty good. There are some other implementations of a binary heap, or binary heap. There's the Fibonacci heap, which insertion can be done in constant time, and deletion can be done in log of n amortized time. So it's not a worst case analysis, amortized case analysis. And finding the maximum can be done in constant time. Then there's the Brodel Q, constant insertion, log base n, deletion, and max. Finding the max be constant. And what I'm going to consider as being impossible. Why is it impossible? Challenge for you to think about. That has constant insertion, constant deletion, constant max runtime. Now, with this D-array heap, because we have this D factor that's out in front, thinking about increasing D is nice because it shortens the tree, but why? But while we're doing that, it's also increasing the runtime for delete max. The sweet spot for this D is actually right around D equals 4. So a binary heap is improvement over the ordered or the unordered array, but binary itself could be improved by increasing our binary tree to have 4 children instead of just 2. Okay, some things to consider with the implementation. Under an overflow, So we want to throw an underflow exception if deleting, finding the max or deleting the max from an empty priority queue. We want to throw an overflow exception if the no argument constructor is implemented and we need to resize the array. This leads to log n amortized time per operation because similar to the array-based the array-based stack and the array-based queue, we had to switch from worst case to amortized case because every once in a while we may have to increase our size. But how to do a worst case analysis, that's an interesting thing to think about. So these are two exceptions you can throw. Also, I had mentioned a few times, we talked about the maximum priority queue, but what about a minimum oriented priority queue? To switch this over, you just simply replace a less called with a greater, and everything else is exactly the same. So you just need to implement a greater operation, which is pretty straightforward to do. Okay, some other considerations. Binary heap is not cache friendly. So similar to the linked list, your nodes can be all over the place in memory, and so traversing a linked list can just destroy your cache and increase the runtime by a lot. Typically, with your page size is roughly about 8 nodes in. You have enough space to store 8 nodes in one page, which means that when you access one of the entries, the computer is going to cache in the entire page, so all of the surrounding things, roughly, the other 7 nodes, and so accessing the other 7 nodes, in relatively speaking, will be basically free to do. But accessing something that's not paged in is very costly. And so there are a couple of variants on the D-Way heap or priority queues that are cache friendly. They do consider the caching in there. So there's a cache-aligned D-Way heap, there's a funnel heap, and a B heap as well, and lots of others. Some other operations that you might want to think about implementing, we had already mentioned removing an arbitrary item, not just the maximum or the minimum in a minimum priority queue. Another one might be to be able to change the priority of an item. So suppose that you insert an item into the priority queue, and then later you decide you want to change the value that's in there. So how do you be able to do that without leaving the heap in violated order? You can implement both the remove an arbitrary item and the change in the priority queue using the helper functions that we've already described, sync and swim. But most implementations assume that you are not allowed to change the priority of an item. It just simplifies it tremendously. So it will make the demand that the keys are immutable. So once they're inserted into the priority queue, that's it. And that the only way that you're allowed to change the priority of an item would be to simply remove the item that you are going to be changing. So you remove that item out of the priority queue. Then you can insert a new item into the priority queue with the new priority value. Typically, you just want to assume that the keys are immutable. It makes your job a lot easier implementing the priority queue. Imagine trying to manage, 1 billion items, and every once in a while, one of those items may decide to just change its value. And detecting this would be is a non-trivial problem. You basically have to run through your entire list, all n entries, and just check: are we still in proper order? Unless you can trust that the client will inform you when priority has been changed, which you should probably not make that assumption. Not assume that the client's going to do a good job there. All right, so to implement immutability in Java, we've already talked about this, but here's a more formal description of it, using the final keyword. So the final means that beyond the constructor, No function is allowed to change this value. In fact, it's a syntax error in Java. It won't even compile if you try to assign a value to n in any function other than the constructor. So it is what it is, and it cannot change. Some other immutable data types in Java are string. So every time you create a string, that's actually an immutable type. So you cannot actually take a string and concatenate another string to it. What it's doing instead is it's taking the first string, taking the second string, and creating a new string with the first one followed by the second one. Integer, the integer object, is also an immutable type. So anytime you have an integer I equal to 2, it's creating an object that an integer object with the 2 stored in it. But when you go to add I plus I, it is creating a new integer object with the value of 4. So every time you're adding together, you're concatenating with these immutable types, Java is actually allocating a new is allocating and constructing a new object every single time. So this is another reason why you want to use integer, capital I integer, sparingly, because it can have cost, a significant cost to add a significant cost to your implementation. Some other ones: double, capital D, double. All of the primitive wrappers, the object wrappers, are immutable. Color, vector, transaction that we talked about, point2D, which we'll talk about very soon. Some mutable types, which are related to some of the immutable, is a string builder. So if you're ever going to be constructing or concatenating a bunch of strings together, it would be best to create a string builder object, which has efficient ways to be able to do that. Append all the entries that, or all the strings or numbers or whatever it is that you're doing to it, and then call toString on that, which will convert it into a string. Concatenating string objects will run in quadratic time. The string builder will run in closer to linear time. It is slightly amortized unless you specify the capacity, the starting capacity to it, and then it's linear as long as you're under that runtime. Stack is another mutable type, so you're allowed to push on and pop off counter. Java array is also a mutable type. Some advantages to using the immutable types: it simplifies debugging, so you know that once the value is in there, that's what it is. The only way to change it is to actually create a new object. It's safer in the presence of hostile code, so when you cannot trust that the client is going to inform you that the priority has changed on an item that's on the priority queue, it's best to make it immutable, and then you don't have to worry about it. Now it's on the client to have to remove that arbitrary item and insert it with the new priority. It simplifies concurrent programming, so a lot of machines nowadays, most machines, have multiple threads. A lot of programming languages have built-in multi-threading or multiprocessor support. So if most of your data types are immutable, this makes concurrent programming a lot easier. Anytime you add mutability where different threads might be manipulating the same mutable object, you're going to run into race conditions where you're in the middle of making this one change, and then this thread decides to jump in and make some changes to it, and then it's left in a state that's kind of broken. Another advantage to immutability is it's safe to use as a key in priority queue or symbol table. You don't have to put assumptions or trust that the client's going to do the right thing. You basically have to force them. But a disadvantage, I already mentioned that with the string, you must create a new object for each data type value. You cannot just simply concatenate two strings together. It creates a brand new string with all of the left and right sides put together. Here's a quote from Joshua Block, a Java architect. Classes, this is speaking about Java, classes should be immutable unless there's a very, very good reason to make them mutable. If a class cannot be made immutable, you should limit its mutability as much as possible. And yes, there is a t-shirt that you can buy that says, I am immutable. All right, next up is, I know we've kind of left off with the sorting algorithms with the quicksort, but I want to add one more into here. You probably noticed it in the visualization, the oralization, of the sorting algorithms that we played, the little YouTube video. There's one called heap sort. So you can actually use the priority queue to sort your data. And so I want to talk through this next. All right, so before you do this, I have some sample code here. It is a sorting algorithm. It's a proper sorting algorithm. My question to you is, what is the name of this sorting algorithm? So we have here, we're getting the length of the array coming in. We're creating a maximum priority queue. And then we're inserting all the items into the priority queue. And then we're deleting every one of the items in descending order. And replacing our array, the ith entry of the array in there, starting at the end and moving back to the beginning. So here is a sorting algorithm that uses a priority queue to do the sorting. But my question to you is, what is the name of the sorting algorithm? Yeah, you can say heap sort, but it is very, very closely related to this other sorting algorithm that we have seen. That's what I'm asking for. What is the name of the other sorting algorithm that is this right here? I'll give you a moment to think about it. All right, so if you need a little bit more time, pause it now, but let's see if we can figure out what this is. So again, what is the name of the sorting algorithm? We have this priority queue that's being created, and then we're inserting a bunch of items on there, and then we're moving them off. So let's look at what this process is doing here. So suppose we have the values, A, B, C, D, E, F, and G, and let's mix them up. So because they're going to come in some random order, we want this to be the final output of it. But let's just suppose that the data comes in looking like something like this, D and E. All right, so we have 1, 2, 3, 4, 5, 6, 7, same number. Okay, so we haven't lost anything. That's good. All right, so let's go through and insert these into our data structure, see what that happens to look like, see if we can, from that, figure out, what is this starting to look like. So the first one going in is a C, so that's going to go in. So this is located at index 1. Let me just change the color so that we can see what's happening here. Oh. Index 1, there we go. All right, so now let's insert the next one. So we've done this one. Let's insert a B, and the B goes in at the end. And then we're going to compare this entry with its parent to see if it's larger. We need to swap them. In this case, it isn't. We're in good order, so we can. So we're good to go. So now we need to insert the next item, which is F. F gets inserted at the end. So this is the index 3. We need to check, is this one larger than its parent? If so, we need to swap them. In this case, it actually is. So we're going to swap these two entries here. So we're going to put the C here. It's a terrible C, and place our F here. All right, so now we're in sorted order. Let's go and insert the A. The A goes in right here, in the 4th position. We compare A to its parent. So its parent is I or K over 2. In this case, it's a 2. A is smaller than B, so we're good. We're good to go. So now G. G gets inserted into the 5th position. Now, comparing G to its parent, so the index here is 5 divided by 2 is 2. G is larger than B, so we do need to swap these. So we're going to swap G and B. So we put G here and B here. And then we need to compare G with, which is not 2, with its parent. So 2 divided by 2 is 1. We compare the two. They are out of order. G is larger than F, so we need to swap these two. So we'll go ahead and do that. So G here and F here. All right, so now we're good to go. So have you seen a pattern quite yet? So we're inserting at the end and then moving it back. So it's starting to look a little bit like insertion sort, where we have an entry and then we shift it back. Maybe shell sort, because it's, you know, skipping by quite a few. All right, so let's add in the next one, D at position 6. All right, compare this to its parent, which is 6 divided by 2 is 3. So indeed, D is greater than C, so we need to remove or replace these two here. So D will go here, and C will go here. And then now we need to compare D with its parent, so it's at 3. Comparing with at 1 is G, D is less than G, so we're good. And then finally we have our E. E goes in the 7th position. So we compare this entry to its parent. 7 divided by 2 is 3. E is greater than D, so we do need to swap them. So E will go here, D will go here. And now we compare E to its parent, which is G. And it is in correct order. E is smaller, so we are good. So after going through all of this, this is what our array looks like. If we were to sketch up what the representative tree would look like, it would have G at the root, F, E, then A, B, C, and D, and go like this. Now notice that the last row does happen to be in the correct order, A, B, C, D, but you know that just happened to be because of the way that we shuffled. So it's not because it's always going to be this way. It just happened to be that way. Okay, so it looks like when we're doing insertion, this part right here, this is starting to look like insertion sort. Up here, so comparing this to, say, merge sort, we have a partitioning element, and the left and right sides are not necessarily sorted, but all entries to the left are smaller, all entries to the right are greater. In this case, we don't have that. We have the greatest entry here, and the smaller entries going down into the subtree. The same thing going down the right, but there's no real comparison between the left and right. So I don't think that merge or quick sort is necessarily the closest thing to this. But insertion sort definitely looks like it. Maybe shell sort. We still have a little bit more to work. All right, so now let's do this. Let's remove. So removing, we're going to be swapping the first with the final entry. And then we are going to write it into the 8th A sub I position at that location. So what I'm going to do, just for convenience, is I'm actually, rather than having another array that we're going to write it into, because this one actually deletes it from our priority queue array, I'm just going to leave it in there. I'm going to allow it to loiter just a little bit, and hopefully this will make a little sense in just a moment. Okay, so let's go through the deletion. This is after insertion. So now let's start deleting things. So when we delete, we take the first entry and move into we exchange it, the first with the last entry, and then need to sync down the new root because we might have violated something. So let's do that exchange. So we have here D. Actually, let me do this. We'll put D here. Write these entries, and then here we're going to put our G. So our G is our maximum item, and we're just going to leave it there. Now D the D in its position here is violating the maximum heap, so we need to correct this. We look at its two children, in this case F and E, find the greater of the two, in this case F, compare D with F. these are out of order, so we need to swap these. So we're going to have F, then D, and then we might need to sink D further down. So we have D here, its two children are B and C. The larger of the two is C. We compare D with C. It's in the correct order, so we're good to go. All right, so then we need to find, so we've successfully deleted the max, in this case G, corrected, so now we're in max heap, and I have this colored in blue just for right now. You'll see why in just a second. Okay, so now let's repeat the operation to delete max. So we're going to swap the first and last entry, so F and C. So over here, F will go, over here, C will go. Oops. Let's color this green, or blue. All right, so now let's correct our maximum heap. We look at the two children of C. We see E is greater. We compare E with C. E is greater, so we need to put E here and C here. And then we need to compare C with its two children. In this case, it only has one child. So E's children are C and A. D's child is B. It has no. Did we lose data? Let's see here. Let's do this. This one has these two children. This one has these two children. And this one has these two, but they have been deleted. So C has no children. Okay. So in this case, C doesn't compare to anything, so it is in correct max heap order. All right, so good. All right, so let's do this. Let's go ahead and remove the next item, the next deleted item, and get rid of that. All right, so we're going to swap E and B. So E will go here, and B will go here. And then we need to correct. Looking at the two children, D and C, D is greater, so and it is also bigger than B. So we're going to swap this, put B here, and D here, DBCA. All right, and B has one child, A, but it is greater than A, so we're good. All right. So we're going to do this yet again. We're going to swap the first and last. So D will come here, and A will go here. A goes there. And then we fix the maximum heap. So C is larger of the two. So we'll swap these two. A and C will go here. All right, we're good. Let's do it just a couple more times. So we're going to swap A and C. We're going to put C here in blue, A here in red. A has a single child, which is B. It is out of order, so we'll put B here. All right, we're good. All right, so now we need to delete once more. So B will go here, and A will go here. A has no children, so it's in correct max heap. And then finally, we're going to delete the max. We're going to swap this for its final entry. Look at that. All right, so now we should match up to what's up here, assuming we did everything correctly. So this, again, this is after insertion. So this is our insertion. And this is after deletion. Now, what about merge sort? Was this similar to merge sort? And again, merge sort is we had a left and right sides that were in sorted order, and then we merged the entries together into proper order. Is this similar to that? I don't think so. I think this is a lot closer to insertion sort or maybe shell sort, in that when we're inserting, we insert at the back and we move them forward as we need. So we're shifting things from left to right to make room for, in this case, a larger entry. And then when we're going through the deletion, we do a swap, an exchange, which violates our max heap order. but then we move the entry from left to right. We sync it down until it's in the correct position. So that seems very, very similar to merge sort. So the answer to this is maybe insertion sort, maybe shell sort, something right around there. But it's definitely not merge sort. It's also definitely not quick sort. All right. So after this, we have another quiz. What are the properties of this sorting algorithm here? So it's the same code as before, not doing anything different there, but now we're asking what are the properties. So A, it can sort the data in n log n using n log n comparisons or fewer in the worst case. B, it is in-place sorting algorithm, which means that it doesn't need to allocate any additional memory beyond maybe log of the size of the entry times some constant c. Again, that was to handle or to account for recursion in the process. So if the function recurses, but the depth of that recursion is bounded by log of the number of entries in there, then that's still considered in-place sorting. C, stable sorting, which means that if you have two entries of equal value, they don't switch sides after they get sorted. They remain in the relative same ordering to one another. D, all of the above. Or E, I don't know. I'll let you think on this. All right. Let's. If you need a little more time, go ahead and pause it. But for now, let's consider this. So what about the n log n number of comparisons? So we saw from the previous that insertion can be done in basically log n time, log base 2 of the number of entries in there. So we can go through and insert every entry, or each entry takes log n, and since we're touching all n entries, that'd be n times log n. Okay, so that's our analysis so far. What about this line of code here? Well, this one we saw that we can delete in logarithmic time as well. It was 2 log n, but that too is just a factor. And we are deleting n entries total. So it would be n times log n there. All right, so we have for this line of code, we have n log n. For this line of code, we have 2 n log n. What about this here? Well, this just allocates an empty array, and then we're inserting. Perhaps we pass in how many entries are in there so that we can allocate an array of sufficiently large enough size. Okay, so this here, at worst, maybe it's linear to it, allocating enough space for all the entries to go in there. All right, so we have n log n plus 2 n log n, and that's it. So A, n log n comparisons in the worst case, technically 2 n log n, but I'll accept n log n as doable. What about in-place sorting? Well, this maximum priority queue is allocating space within it, an array of number of entries to store all of them. So technically we are allocating an additional n space, so this is not an in-place sorting algorithm. All right, what about stable sorting? Turns out no. Stable sorting, this is not stable. This is not a stable sort algorithm either. And the example, counterexample, was in the when I mentioned we can insert keys, duplicate keys into the priority queue, and when we go to delete or find the max, we don't really care which one's which. We just delete one of them. So this is not. So in this example, we could insert in the wrong spot. Could insert into. So, for example, here's our root, and it happened to we go and insert an A, and that might insert because we have somewhere down here an entry that needs to go in here. Well, this first A can actually be inserted here, okay? And then a second A, which actually comes after the first one, because this row is full, it might go down this left subtree here. So it's over here on the left side, and as we're deleting, there will come a time when we have so here's our root. We go to delete our max. We need to figure out, does A2 or A1 go up to the root? If we pick one of them, say A2 gets moved up, then we've broken it. Okay, so alternatively we could put A1 up here, but what happens if instead of our example turning out like this, instead we had A1, this one, got inserted here, and then A2 got inserted afterwards. And now if we follow the same logic, A1 is here, A2 is here, and in this case A2 would go up there, so that's broken. So in this case, it is not in place, it is not stable, it is certainly not all of the above. A would be the correct answer, although 2 and log n would probably be a better answer for it. So A is the answer. All right, so how can we further improve this? Well, we can actually, instead of allocating an additional space in the maximum priority queue, we can just simply use this same A to do our sorting. Now, one small catch, we have the 0th entry in A that we are ignoring in our heap sort. So we'll have to kind of pretend that we shifted over. There are some ways to be able to do this in constant time. We're not actually shifting it over in linear, but even if we did have to shift over linear time, linear fits into the n log n, so we're still good here. All right, so for now, just pretends that it is shifted over, but we can account for that shifting, or even just reworking our math to where we start counting at 0. But the basic plan for in-place sorting version of heap sort is to view that input array as the array that we're working in. And so we're going to treat it as a complete tree, as it is, but note that it is violating our maximum heap. So as an example here, we have an E, which is a parent to these two children, but L has a key that is larger than E. So there's definitely a violation here. So what we'll do is we'll first pretend that this is a complete binary tree, and then we'll go through and systematically fix it up to turn it into a maximum heap. So we'll turn this data structure, so here's the tree representation of this array, into this here, which is a proper maximum heap, and then we'll continue on with the successive deletion of the maximum items, putting them into the, swapping the root into the last open position, or the last entry on the tree, and effectively deleting it, but we're not going to null it out. So similar to the example that I went through, where I drew the colors or the letters in blue instead of actually deleting them, we're going to leave them there. And then in the end, the array will be in final sorted order. So let's walk through the demo of doing this. We need to construct the max heap given the input the unsorted array. And so what we're going to do is use a bottom-up method. We're going to assume the array entries are indexed from 1 to n. Again, accounting thing. We could just renumber things, make it 0, 1, or we can shift it if we have the space. And then we're going to, then after constructing the heap, turning it into a proper heap, we're going to perform a sort down process, which repeatedly deletes the largest item, not removing it, not nulling it out of the array, but just exchanging into the last position. All right, so here is the demo. So given our sort example input, here is the tree representation of this. And what we're going to do is go through and find all the violations. And the first violation, potential violation, will be the first or the last node with at least one child. Okay, if it has 0 children, then it's not in violation, so we're good. We're going to find the last one that has at least 1 child, and then we're going to check if it's in violation or not. And what we're going to do is, if it's in violation, we'll sink it down into its proper spot. So in this case here, we look at its 2 children. So E has 2 children, L and E. L is the larger of the 2. We compare E to L. E is smaller than L, so we need to sink it. But now E is at the bottom, so we're good. So all the way up to this entry here, we're good to go. But we still have a few more to work on. So we'll look at the next one, next item. Here we're going to check the 4th item. So we find this larger of the 2 children. In this case is P. We compare T to P. T is greater than P, so we don't need to do anything with T. It just stays put. We go to the next one. We find the larger of the 2, which is X. We compare R to X. R is smaller than X, so we need to sink it down. At this point, it has no children, so it's in proper max heap order. So everything back up to X, not including O and S, but everything X and down, from here down, that's proper max heap. All right, move on to the next one. Then we have an O. The larger of these 2 is T. It is smaller than T, so we need to sink it down. And then we compare it with the M and the P. P is larger, and so it needs to sink down again. And then here it has 0 children, so it's in proper position. And the last one is the root. So we find the larger of the 2, X, and then we'll exchange. Find the larger of the 2, R. S is greater than R, so it's going to stay put. And finally, at this point, our array, which was it was a complete binary tree, but it was not yet a max heap because there were entries that were violating the invariant of a max heap. But after doing this heap construction, we're able to turn our arbitrary array into a maximum heap. So this is a proper max heap. And now we can do the sort down process of putting it into sorted order. So to do this, we're going to exchange the root with the final entry, and then we'll sink this E that moves up down. So again, we'll look at the 2 children, find the larger of the 2, compare that to that, the E will come up here, we'll compare E with T. E is smaller, so it'll sink down, and then we'll continue through that process. But when we move the X into that last position, we're going to still decrement N, so this number of entries left in the max heap has decreased, but we're going to leave it there. So I've indicated that with coloring it gray, but I've detached it from the max heap. And then we just continue on. So we swap T and E, these 2 entries here, sink down the E into its proper spot, and we leave T alone. We swap S and E, we sink E into its proper spot, and now S is in its position. And then we do the same thing, R and M. And M gets moved down, R is in position. We just continue, 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 continue. And finally, A swaps with itself. It's in sorted max heap order. So we are good to go. And if you look, our final array, ignoring the 0th index, this is in sorted order. Ta-da. So now you've seen yet another sorting algorithm. Okay, so during the construction, we need to just sink down items, and this is very simple to do. In fact, it can be done in 2 lines of code. We iterate starting at the last entry that has at least 1 child. Starting from there and going back to the root, we're going to continually sink that particular one down. And then once this finishes, we just need to do the sort down, which looks very much like the del max function, just without the nulling involved. So what we're going to do is exchange the root with the last item, decrementing after we do the exchange, and then we're going to sink the root down. And that's it. So just those 2 lines of code gives us a heap sort algorithm. So to sort using heap sort, we take in an array of comparable items, we do the heap construction, and then the sync down process. And both of these use exchange and sync and the less that we've seen all before. So nothing new there. And that's it. Here's a trace of the heap sort algorithm at work. So here's our input, and then every data item that is accessed is indicated as a letter, and then they're left in their final position. So all these entries here were not touched. They weren't even looked at. So this is going through the process of syncing down, or the heap construction. So we have to compare E with its two children, and this one's the larger of the two, and so that gets swapped up. We compare T with its two children. Well, P is the greater of the two, but T is greater than the greatest. We compare R with its two children. X is greater, it's greater than R, so we swap them, and so forth. And once we get to this point here, we are in max heap order, and then we go through the sort down process, which is this right here. So every entry gets moved into the final position, and then we sync the root down to its correct spot, and then finally we're left with the sorted result. Alright, so you've seen this before. I'm going to go ahead and play it. First, make a prediction. Which ones are going to do the best? Are they all going to, or all, or some of them going to do exactly the same? Which one's going to be the worst? And ready, set, go. Oh. So this one finished the quickest, the second, and then these two were basically about the same. So I'll restart that again. Let's look at this. So this one was in reversed order, and this one was random. Oh, no, sorry. This is nearly sorted. This is reverse. This is random. So after the first heap construction pass, these two looked very similar to one another, so I'm going to play it again. So after this finishes with the heap construction, if you compare the two results before the black lines start coming in, they actually look very similar to one another. These two over here, let's look to see what's happening here. So notice that this already is in proper heap order. So every entry is larger than its children. And so we're just running through, there's no syncing happening here. And then finally it starts to move all the entries down. And somewhere in the middle it starts to look like these two here. What about this last one here? Well, the last one is kind of a special case because we only have a few distinct values. So moving entries doesn't, each entry does not have to move very far. Here, as soon as we start deleting and we're exchanging the maximum item with the smallest item, that small item has to move back down roughly about halfway. It's skipping quite a bit, but it has to move about halfway down. Here, how far it needs to move down is a lot less, so it spends a lot more time up here before it runs into some entry that's in proper order. So for distinct values or few distinct values, few unique values, this algorithm runs pretty well. For reverse order, it doesn't have to do any work on the first part of the heap construction. It's just on sort down. Whereas with nearly sorted or random, it's doing about the same amount of work. So that's why they end roughly in the same time. All right, so the analysis of this algorithm, heap construction uses fewer than 2 times n comparisons and fewer than n exchanges, or at most n exchanges. Proof of this can be seen in this sketch here. So we're just going to assume that the number of entries is 2 to some h plus 1 minus 1. This h is the height of the tree. So we're just assuming that we have a complete binary tree with the bottom row is completely full. But this works even not within this construction. And so for each entry needing to sink down, the maximum number of times that we have to compare or do an exchange is bounded by the height. So here we have h, and then we have 2 times h minus 1, 4 times h minus 2, 8 times h minus 3, and so forth. And when you sum all this up, this is less than or equal to 2 to the h plus 1 minus 1, which is just simply equal to n. And since when we're doing the sinking, we have to compare the two children and then do the comparison with the parent and the larger of the two child, that's where the 2 comes in. But the number of exchanges, the number of times we have to go down, is bounded. We only have to exchange at most log base 2 of n times. So we have a linear runtime there. Now, one thing to note is the left side of this is a little bit trickier. I kind of brushed over this just a little bit. For more information, definitely see discrete, figuring out that left-hand side. All right, so here's a proposition. Heap sort in total uses less than or equal to 2 times n times log base 2 of n comparisons and exchanges, though the algorithm can be improved to tilde 1n log base 2 of n, but no such variant is known to be practical. Like, you can do this theoretically, but the amount of work that you're doing is it's really hard. So 2n log n is a good number, a good analysis for this algorithm. All right, so some significance. There is an in-place sorting algorithm. We talked about it with n log n worst case runtime. Merge sort is not in place. It requires linear extra space to the auxiliary to be able to exchange in there. There is an in-place version of it, but it too is also not practical. Quicksort is not guaranteed to be in place. Quadratic runtime in the worst case, although the probability of that is really, really, really low. In log n worst case, quicksort is possible but not practical. But heap sort is able to do all the stuff in place. You just use the same array, you do the heap construction, and then the sort down. So no extra beyond a constant number of more memory is needed to perform this operation. Heap sort is optimal for both time and space, but the similar to quicksort and merge sort, the inner loop is longer than quicksort's, which is kind of tricky. It makes poor use of caching, so you can use a more advanced heap algorithm that is cache friendly. And one other thing, it's not stable. I gave the example earlier that heap sort is not stable. So we are able to get guarantees on runtime and in place. So in log n, in the worst case, it is in place. It is optimal both time and space, but we're still not quite hitting that fully stable algorithm. Which brings us to intro sort. And this is what one of the videos I'm going to have you watch is talking about. So the goal of intro sort is to be as fast as quicksort in practice, but in log n in the worst case. So it's not the average case, or the highly probable case, but the worst case, we want it to be in log n, and we want it to be in place. And to do this, we're going to run quicksort, cut off to heap sort if the stack depth exceeds 2 times log base 2 of n, and then cut off to insertion sort when our n gets small enough, so say 16, that we'll switch off to insertion sort, which has a low overhead. Because the size of the array is small, even though insertion runs in quadratic time, the n is really, really tiny. And so in the wild, this is the standard sorting algorithm, STL, C++. Also, the .NET framework, last I knew, uses intro sort. All right, so in summary, we've seen this table before. I've kind of filled it out just a little bit more. So we've seen selection sort, which can be done in place. It's not stable, and its worst case is 1/2 n squared. A couple of remarks over here. It uses n exchanges. We've seen insertion sort, shell sort. Again, nothing's known about its average runtime. Good research area. It's very small. The code for doing shell sort is really tiny. So shell sort is often embedded even into CPUs because it can be. Has sub-quadratic runtimes, which is kind of nice. We've seen merge sort, which is stable. It has an average and worst case of n log n, but it's not in place, at least the practical implementations of this. It is guaranteed n log n runtimes, so that's nice. Tim sort is kind of an improvement on merge sort that takes advantage of pre-existing order, so closer to the natural merge sort with some other optimizations in there. So in the best case, we have linear runtimes, but in the worst case, n log n. It is stable, but because it's merge sort, it's not in place. Quick sort can be done in place, but it's not stable. It has an average runtime of 2 n log n, natural log of n, but the worst case, highly improbable, is quadratic runtime. This is, in general, the fastest sorting algorithm in practice, but not for every input. So it's important to know, again, what does the input look like. If you have a sense of what the input is going to look like, you can choose the better runtime algorithm for this. The three-way quicksort, so using the median of 3, improves upon this when there are duplicate keys. And then our heap sort, which we just saw, can be done in place. It is not stable. It has a best runtime of linear, but a worst runtime of 2 n log n guaranteed. So that's kind of nice. The holy grail, again, of sorting would be able to still have the linear runtime in the best case, n log n in the worst case. It can be done in place, so you don't need additional memory, but that it is also stable. So still more work to be done. All right. I'm going to skip that section. Actually, I just need to remove it from the slides. But that is the end of the priority queues lecture. I will be posting this video to Moodle, and I will be also posting a couple of other things in missed it. Where'd it go? To the video on intro sort that I had mentioned last week, that you will be watching and answering some questions too. So again, I hope you're having a great fall break, and I will see you when I return from Amsterdam.